Where's John Bush? Oh, right. Okay.
So welcome back, everyone. So we're very happy to have Jun Zhang now speaking. The reason he's talking about this is he got inspired by John and Eve's work on quantum mechanics, and we had to convince him not to do experiment on the Big Bang in the lab at Courant. So instead, he had to work on this.
Fish.
Yeah.
Locomotion. Great. Welcome back. So today I won't talk about quantum mechanics because problem is killed already. Here is a set of experiments I want to show you that concerns animal locomotion, flapping flight or swimming. Those bunch of experiments were carried out at the Courant Institute. You know that we have a lab in the lobby if you happen to be there. Okay. First, I want to acknowledge the people who really did the work. Leif Ristroff, he was a visiting student from Cornell, but now he just came this month to our institute as a postdoc. And Thijs Snipper from Danish Technical University, and they both visited for a very short time, but extremely productive. They are technically very capable and clear-minded. Also, they come with a lot of common sense.
Does he come from Copenhagen?
Yes, Thijs is from Copenhagen, but he's avoiding the old issue anyway. Yeah, that's a good point. Okay, so I'm discussing today about schooling. That's schooling for fish. They swim together. That's flocking, many birds. Okay, so here you see a fish ball. Like they rotate probably in this direction. You can look at the orientation. And there's a guy just waiting for the chances. Okay, there's probably a social reason for these guys to move together. It's like us sitting in this room for some reason because we like each other. We are sitting under one roof, and these guys they fly together, and just for this moment they make this formation look like a rabbit if you see it. Okay, right. So it's possibly they do such a thing as a social behavior, but we also want to know to what extent this is a physics problem. Say if you remove their mind in some ways, do they still do this? Or they behave differently, very differently. It's like us, we like each other, we sit in this room, but we don't sit on top of each other, right? So that's a bad analogy, of course. And here, the interaction between these guys, certainly social, not very physical, right? You can't imagine these guys putting too much attraction force or some physical force onto the individuals behind them. Okay? So, let me introduce something little basic about swimming and flying. So that's a nice illustration by Asher, who did some 60 years ago. That's a sky and water. He unified two locomoting behaviors. One is flying, one is swimming. You see, this is the same problem. For him, from this artist view, he got it right. Basically, when we treat this kind of problem right down all the relevant equations, we have a reciprocal motion, and we are dealing with a continuous medium surround these guys. Okay? So this intuition was perfectly correct. And the second version of that is this. Okay? So it's a beautiful work. And for fish and birds, they swim or they fly around the Rayleigh number 1,000 above. Sometimes they can go to 1 million or more. Depends on the size and the speed, of course. Okay. And I like to show this slide. Even though it has been suspected for swimming fish, they generate this so-called particular wake structure, this inverted Van Karman structure. I will show in the next slide. This has been long suspected for many, many years, but until 1997, people for the first time visualized it in a float tank. That's the tail of a fish moving this way and leaving a characteristic wake structure that looks like this. So you see eddies kind of regularly spaced, okay, in this direction, and then they slowly die out by diffusion. Okay? And, okay, if you take a cut, horizontal cut, through this wake, you see this so-called inverted von Karman strait. So if you focus on two adjacent eddies, this guy is going this way, and then you form a path like this. And then you have another path like this from previous strokes. It's like this guy is sending puffs of water, fluid, in that direction, so you can gain momentum in the opposite direction. Okay? So this is, I count as inverted strait. This is compared with this classical von Karman strait. And when you look at this case, two adjacent ones, you see paths pointing towards the body, the solid body. So that says this guy will slow down the fluid comparing to the far field flow. Okay? So that's a comparison. Some people see the direction correctly. Some people always tell me they look exactly the same. Then, okay, that's your problem. Right. Okay. That's the same. Okay. So we did one experiment studying flapping flight, basically taking a rigid plate, symmetric, and flap it up and down with a controlled frequency and amplitude. And this guy takes off and leaving this vortex strait, just like what I mentioned to you, this inverted von Karman strait. Okay. So you saw the fish from the experiment with a real fish, and you see this artificial bird that flap through a fluid and leaving the same wake. So Asher was really correct in the sense these two, flying and the swimming, is the same thing, basically. Okay? You generate this vortex strait, identical. And Salas and Mike, sitting here, they have done some simulations studying the nature of this bifurcation if you have a symmetric wing, and how it takes off from kind of locally reciprocal motion, and how that takes off. The question is if the bifurcation is subcritical or supercritical, and so on and so forth. And also the importance of the mass of the wing compared to the fluid, and so on. Okay. So let me go back to the topic, to the title. What about the interaction between many locomotors, swimmers or flyers, okay, fish or birds? So there has been some theory, maybe a lot, conjecturing, guessing what kind of interactions you have between swimming fish. For example, this 73 paper by Weiss, okay, he conjectured that because each fish will leave these puffs behind, you have a jet behind, this guy wouldn't like to stay, the guy behind wouldn't like to stay right here, but rather stay somewhere in the middle between the two fish. So likely, they will form this kind of a diamond-like pattern. Okay? That's a conjecture. So far, I haven't seen evidence of this. It can be done, probably, but you have to bear the fishy smell in the lab. I haven't seen anything like that. Also, another group, Leo, where was that? He was at Harvard at the time. He was studying live fish behind the cylinder, so the flow is going this way. You have a von Karman strait, very likely, and this guy would like to interact with the vortices, right, around this. They even put a dead fish behind the cylinder. They found that temporarily, the dead fish can even gain a momentum to move forward, to be close with the cylinder, just over a short period of time. So there has been a lot of studies, indirect, and here is more about some reasoning, and not experimental work. Also here some social study, I would say. By Vishek, he studied basically the flocking behavior of individuals just by visual clues. So you have a simple toy model. You have an individual, just look at your neighborhood. Wherever you go, I will try to average out your motion and try to follow up with that vector. And then slowly come to our experiment, our study. I would say the minimal school or minimal flock would be 2 locomotors. Just look at the very basic, how 2 individuals interact closely with each other. And you have heard about aerodynamic drafting or hydrodynamic drafting. Okay? So if you ride a bike like this, okay, you don't want to be the leader because your resistance is higher, and you want to, stay behind. Of course, you don't get the money in the end, right? This guy wins. The same for racer cars. This guy has a low drag compared to this. Right? And here, there has been a lot of experimental studies studying the drag on cylinders and rigid bodies. That's one of the experiment. You have 2 cylinders, and you have an open flow going from left to the right, and you measure the drag precisely. It's always the case that you have a high drag for the leader and a low drag for the follower. Okay? So never, ever any other situations. I should point out that when you move this guy close to the leader, the drag on this guy will be reduced slightly. But still, you have a high drag and a low drag. Comparatively, that's always the same. Right?
Regarding the radius, how close does it need to get this effect?
Within 1 body length, I would say. Yeah, roughly. There's a term called the wake splitter effect. So you can also add a flat plate extending from the rear side of this cylinder to reduce the drag for this guy. Right? So we will come back to this issue. Right? Then because of this solid study from solid bodies, rigid bodies, so biologists who study group motion and for animals, they basically assumed this leading bird or leading fish somewhere out there, they have to work harder than the followers. Okay? There's no argument, but we do want to study this in the lab to get numbers at some point a few years ago. Then we started to put a fish in the water tank at Courant, and this guy, indeed, if you have a laminar flow, it will orient itself, try to compensate the motion. It's like I put you on a treadmill, I switch it on, you will automatically, by your instinct, you try to compensate the motion I impose on you. Right? So this guy moved forward, but he's not a great collaborator. It hides somewhere here, and you want to escape. It won't stay nicely and flapping and swim in a fixed laboratory frame. So it's not a great collaborator, and this guy we use called a giant dino. It's only like 2 centimeters long. I don't know why there's the word here. Right? Anyway, so this guy is probably too complicated, so we decide maybe a good collaborator is a dead fish. So we kill it. At the same time we kill it, we try to keep the flexibility of this guy, and we try to reduce, say, the lateral dimension, make it even thinner, and keep the extension this direction or this direction, say. Okay. What is that? That's a flag. Okay? If you reduce the size, keeps the flexibility, keeps the extension, and then that's a flag. So if you keep a flag in the water tunnel or in a wind tunnel, you have a wind blowing this way. So you want to study if that guy flaps. We know flag flaps on building tops. And we can regard that's some kind of a ground state of active swimming, this kind of locomotion. Right? So hopefully we can understand in good details about passive swimming. We call it passive swimming. Okay? Because there's no activation. It's just physically, there's instability when it flaps. Right? So hopefully, when we understand better about this passive swimming, we can address a little more about active swimming, the real swimming problem. So here is a flag. The flag is further reduced to a thin silk thread or rubber band. So that's only a few centimeters long. This size is exaggerated. The water tunnel is actually a flowing soap film. Okay? This a big flat soap bubble. It's moving from here to here. So you have a water tank. You have soapy water. You can control the flux, so you can control the speed quite precisely. And here you have two nylon lines, so the soap will run laminar this direction. Okay? I should point it out, a soap has been a nice object to play with, but has been a serious object since this guy put his hands on this soapy water. Okay, that's Richard Courant playing with really soap bubbles with different frames. He was studying minimal surfaces, right, with different constraints. And here, if your vision is good, he was busy designing the logo for IMPA. You see that here? All right. That's a Mobius strip. I don't know which one. Actually, I don't know which one came first. Right? This is the logo. And Eve sitting here, and he introduced motion into the soap film, not a static object anymore. I couldn't get a better copy. I have to ask you for a real one, better one. Yeah. So here's a plume going up in a vertical. I guess it's a vertical stratified soap film. And then later on, people study two-dimensional turbulence and so on and so forth by many people. Garib, Rutgers invented this particular soap film I just showed you. And then Bush, John, you did some natural convection on this, right, at some point. It's a long list of people. Okay. So here, going back to the single flag, so you have a fixed point here. You have a filament here. The soap is going this way. You have natural flapping. That's a high-speed recording played back slowly. Okay? So this wake structure is a little peculiar. It's not in Von Karman. It's not inverting Von Karman. It's like a ribbon, and you have small eddies generated from this common homosync instability. And then it changes sign every half cycle of this flapping. And here is a movie showing how the filament moves if you eliminate the filament only and ignore the fluid. And here you see that even this guy is confined into a two-dimensional plane due to the inextensibility of this guy and also the flapping motion. You see a figure of 8 motion at the tip. Okay? So you see that with the flapping swimming fish as well. Okay? So with a single fish, single flag, we already saw some surprise. One surprise is that under the same flow conditions, same flow speed, the same flag, you can have two stable states. One is that a stretched, straight state. That says the flow will extend the flag and make it stable. If you perturb this whole thing with small amplitude, we'll quickly come back to this steady state. Okay? With a Von Karman like straight trailing off from the end when the two boundary layers meet at the free end. Okay? So for small amplitude, it's very stable. When you perturb it with a finite amplitude large enough, it will be flapping like a flag you just saw. Right? So we put an analogy, we call this guy as a gliding state, and here's a swimming, flapping state. Okay? Another surprise we found, actually, Mike worked on the theory for quite some time, is that the mass of the flag is extremely important. If the mass of the flag compared to the mass of the surrounding fluid is too light, there's not enough inertia to keep this flag sustain its flapping motion. Okay. And then, let me go back to the minimal school of two passive swimmers here. One on the top, one at the bottom. Okay? And now you know that I'm going to measure the drag on each of the body. So inserting a 2 centimeter small object in a flowing soft film and measuring the drag force is a little challenging, but you can use this Cavendish's technique. So you have a support here going through the soft film, and then at the point they meet, you put your flag there. And now whenever you have a drag here, the drag force is transmitted to the supporting cantilever. You will have a slight bending downwards. So outside of the soft film, for the support, you have a small mirror. When you hit the mirror with this laser pointer, the light dot will be, you have an amplified signal somewhere else. So the light path is often like 5-6 meters long. So you can get very precise measurement down to 1 millionth of Newton, or something like that, a few dime or sub-dime. All right, so that's the force measurement.
In your experiment, how did you control the flapping motion, amplitude, and frequency of flapping?
It's all flexible. I don't control anything.
It flaps naturally?
It flaps naturally. It's a natural instability. Right. What you control here is you give a fixed flow speed, and right, and all that. And the width of this soft film laminar tunnel is like an order of 10 centimeters or up to 20 centimeters. Right? And here, I want to emphasize the force we measure is the time average force. So in the experiment, basically the cantilever has a little attachment that is soaked into that's a dash pot, soaked into a viscous fluid. So it filters out the high frequency flapping the frequency. You measure time average drag. And here, that's TICE in the lab. That's a soap tunnel that's going vertically like that. And I remember we counted at the time when you need to measure the flapping amplitude, frequency, and the forces, and the TICE need to make 15 different small instruments to work at the same time, which is not very trivial. Okay? That's why he needs this hat. So for good luck, he wears this hat in the lab all the time. I don't know why, actually. And here's the movie of these two flags. Here is the first flag, which is fixed here. Second flag is fixed here. Okay. It's just a movie of that. Let me show you a photo. Okay, a single snapshot when they're separated by almost one body length. So you see the wake structure is not as clean as one with a single flag. Okay? And then when you take a strobe photo of this flag, you see that they really undergo periodic motion. And one thing you probably notice is this guy has a smaller amplitude compared to this. When you change the row, you move this guy up in front of this, they change. Okay? Then the leader always have small amplitude. The trailing guy, the follower, always have bigger amplitude. Okay. Then some measurement of the force. Now you look at me. Here's the first flag. That's the second flag. Here I have a little gap. Right now the gap is 0. Okay. So I'm going to increase the gap slowly. This gap is normalized by the body length. That's a gap normalized by L here. So that's the distance between these guys. That's a normalized drag. That's a drag measured divided by the drag of a single flag. So one is a single flag. Here's a 2 independent flag for the drag. Okay. Very much to our surprise. So the leading flag has a low drag compared to the follower. And the drag, when the gap is almost 0, you can have almost 50% of the drag reduction. That's a huge cut in the drag. So as a group, as you can see, when they're really close, you have some benefit that when it's below 2. And over this range of gap, there's a punishment. So the total drag is higher. Right? And then when they are put further apart, they become somehow independent. So they approach to 1 as individuals. The sum is about 2. So they don't talk to each other that much. Right? So that's a surprise. So we call it right now. For the first time we saw 2 sort of identical body to start with. You see low drag for the leader and the high drag for the follower. Okay? So if you want to reduce drag, in this case, if you are flexible, you stay up in front. You might ask, what about alignment? Do you require perfect alignment one after each other, or it's allowed to have a little shift? The answer is you can move about, misalign them. For example, you fix one flag here at this guy, and then you move the another flag around. When you measure the drag, that's a 2-dimensional map of the drag. So the blue color means if you move, if you are in the neighborhood of another flag in the upstream position, this means you have a drag reduction, always. Right? And here, if you are behind this flag, the red color means you have a high drag. So it's a big area, you have this effect. Okay. At the same time, as I mentioned, amplitude, the amplitude have quite a similar map compared to this one. So if you create the third map, dividing drag by the amplitude, you get a fairly uniform map. So that means the amplitude and the drag is very closely coupled, related. So that also says if I can explain why they take on different flapping amplitude, I should be able to explain this inverted drafting, okay? Inverted drag relationship. Okay. So going to fluid textbook, first chapter, you see the drag for high Reynolds number. By the way, I should mention the Reynolds number is like a 10 to the 4, some order like that. It's very high. So you have a drag coefficient here. You have a fluid density and the flow speed. These quantities are fixed in all cases. Only thing that is different is this area, which is amplitude. Okay. So the amplitude, they look like this over time. You see the envelope, this is smaller and this is big. I try to explain what's going on. To start with, you have one flag that's flapping happily at this position, and then you bring up the second flag into the wake. Before you have this oscillating wake from this guy, now you cut into the wake, you limit the sloshing motion of the wake. So you narrow down the wake. And also this flexible, the later part of this leader lives inside your wake so that you bring down the amplitude of the leader. When you have a smaller amplitude in the flow, so you have lower drag. And as for the second guy, this guy experiences the wake from this leader, which is already oscillating. The flow speed encountered by the second body is basically the same order. It's only decreased by like 2-3%. So you have a natural frequency, you have an oscillating wake, you have a resonance effect here that brings the amplitude bigger. And then the drag is increased. Okay. I still have 10 minutes? More? Okay. All right. So we have a foot comma. I just explained to you why we have this inverted drafting. Anyway. All right. So how about more flags here? We put actually more, like 6 flags, so the phenomenon is quite robust. Say that the first flag always has lower drag compared to the second. But the later ones, they may drop at some point. Okay? Depends on the gap. So the reason is that after many flags, the flow speed encountered by the later ones will drop. So the U square then drop dramatically. Okay? Just let me show you the movie. It really happened in the lab. Okay? And here's an instantaneous snapshot with the flow field. As you can see, it's quite complicated, quite messy. Oops. I told you about the inverted drafting is largely due to the modulation of the wake. So let's do a little more work on the wake. Let's bring something, say, a fixed wake splitter, a rigid plate in the downstream of this flapping flag. Okay. So this we have discussed, and this we have discussed, and this one we try to bring a splitter, try to cut into the wake of the leader to narrow down the wake and to narrow down the amplitude. See, to compare this case and this case, who does the better in cutting down the drag? Okay? So the number comes like this. Again, that's a streamwise separation normalized by the body length. Here's the drag here. You see for the flag and for the splitter, for the drag on the flag, it goes, you have 40% drag reduction. And then slowly, when you move away the splitter, it recovers almost to 1. Okay. So that works over a distance like 30% to 40% of the body length. Maybe that answers some of the question you had. And then this is compared with the flag and the flag case. You see, with two flags, you have a better drag reduction for the leader. Okay? So both data set is for the drag on the leader. So here you see that it works over a longer distance. The drag reduction is more significant. Okay? So that's one thing. Also, imagine we have a case of one big fish, or one fish is more vicious than the other, try to catch the little fish here. So here you have a flag, a flexible flag, and here you have a driven plate that is pivoted at the tip in a controlled fashion with a finite amplitude and frequency, and see what happens there. So this is a little challenging experiment. So Thijs Sniper brought an oscillator here. That's an oscillating motor from Denmark all the way to New York. And then we did the experiment together. Okay? And here is your leading flag. So again, I'm going to measure the drag on this one and see to what extent this guy, the active one, that is sitting downstream of the flow, see if this guy can have any influence on the flag sitting upstream. Okay. The first thing you notice is that at some frequency and amplitude, you can narrow down the flapping amplitude greatly. Okay. That's a good indication about low drag. Okay. Here, I want to take some time. So you can indeed control the upstream body from behind, from downstream. You can synchronize, you can realize synchronization between the active flapper behind and the leading flag. But you need certain amplitude. Okay. So here says, here's the modulation frequency of the active flapper. You can only realize synchronization at a frequency, modulation frequency, that is smaller than the natural frequency of a single flag. Lower, so below 1. This FP here is an indication, is a frequency you get when you have a wake splitter that is in stay put. Okay? Doesn't move. At that frequency, you only need 20% of the flapping amplitude to realize perfect synchronization. Away from this frequency, you need a higher amplitude to realize synchronization. So you can control the upstream flapping body. Below this amplitude, you have a beating motion. Basically, you have a beating between this frequency, between the modulation frequency and the natural frequency. It jumps back and forth. Okay? You have this kind of envelope. Okay? Then let's look at the drag. The drag is also has a monotonic function. We could realize a drag reduction of almost 60%. So here is basically in the neighborhood of 0.3, 1/3 of the original drag. You probably know that if we watch the competition of Olympic swimmers, if you can reduce 0.5% of your drag, that's a big deal for Phelps, right? For these guys wearing this high-tech swimsuit. Okay? Here we are talking about more than 60% of drag reduction, okay? But for flexible bodies. Okay? And then this guy monotonically go up and diverge at some point. But here, outside of this window, we don't have synchronization. It's a little messy outside. All right. What happens? Okay. I'm ready to conclude. So if I could remind you about this classical hydrodynamic drafting, the leader has high drag, the follower has low drag. You can imagine they can easily form aggregates. There's a natural tendency. They form clusters. But with flexible bodies, because the leader has low drag, the follower has higher drag, they don't want to form closed aggregate, or the aggregate is not stable. Okay? But we have to pay attention. Here, so far, we have studied, for example, this case, is 2 passive swimmers, not really active swimmers. So we still have not yet answered the question that we asked at the first place. With active swimming or flapping animals, what is a drag relationship? Which one has low drag? Which one has high drag? We don't quite know. We still don't know. So we have more work to do here. Right? It's still an open question. Right? And here I list quite a few papers we published, including a rejected paper I'm still working on. If you want, I can send you a copy. You can find the PDF files on my website. In physics, I happen to stay half-time in the physics department of NYU. And here comes the big thanks to the organizers, to people like you sitting here after lunch. Thank you. Yeah, John.